This video explores the question, how does a rigid body, such as this yellow box, move once it is set into motion? For the sake of simplicity, we make these assumptions. The center of the body is fixed. There are no extra forces, and the mass of the box is concentrated equally among its 8 vertices. Since the center is fixed, the only possible movements are rotations. A rotation has a unique fixed line called its axis, shown here in blue. We assign a weight to this line proportional to the speed of the rotation and call the result a velocity state. A velocity state omega brings the points of space into motion as follows. A point P moves perpendicular to the common plane of omega and P with a speed proportional to the distance between them, as this picture of two-dimensional rotation should make clear. This produces a velocity vector at P. Define then the momentum at P to be the joining line of P and V, weighted by the mass of the point. The momentum state, sigma, of the body is then the sum of all the momentum lines of its mass points, in our case, the 8 vertices of the box. Since the momentum lines at opposite vertices of the box have equal but opposite directions, the sum of such a pair is an ideal line, or line at infinity. This yields 4 ideal lines, whose sum is again an ideal line. Hence, the momentum sigma is an ideal line. As a placeholder, we draw a red line through the center that stands perpendicular to the planes through sigma. We note in passing that what is usually called angular momentum is just a linear momentum that is carried by an ideal line. That is, all momenta are linear momenta. Because there are no extra forces, the momentum state sigma remains constant throughout the motion. We say it is conserved. There are 3 special cases in which the velocity state omega also remains constant. Otherwise, omega changes continuously in order to conserve the kinetic energy of the motion. The 3 special cases can help understand the general case. They arise when sigma passes through the center of a face. The energy of a moving mass point increases with its distance to omega and decreases with the rotation speed. Hence, for a given kinetic energy of the body, rotating around the largest face has the slowest speed, while rotating around the smallest one has the fastest. For any velocity state omega, you can find a speed s to produce a given kinetic energy. Then, on each omega, mark off a point at distance s from the origin. The resulting set of points forms an ellipsoid, the inertial ellipsoid of the rigid body, shown here in white wireframe. It was discovered by the French mathematician Poinsot in the 19th century. Its 3 principal axes correspond to the 3 special cases we already considered. Once the body starts to move, omega traces out a closed curve on this ellipsoid, called the pole Hoda, shown here in cyan. But that's not all. In the course of the motion, the ellipsoid rolls around on a fixed plane called the invariable plane that is perpendicular to the red momentum line. The point of contact of this rolling motion coincides with omega and describes a curve on the invariable plane called the hairpole, shown here in green. It is generally an open curve, in which case it fills in an annulus in the invariable plane. Considering other rigid bodies besides the yellow box shown here doesn't produce any new behavior, since any rigid body is dynamically equivalent to some box of this kind. If we remove the constraint that the center of the body is fixed, we obtain a motion that includes translations as well as rotations. These motions are naturally more complex, especially in non-Euclidean space. We can ask, are there analogs to Poinsot's analysis of the motion? Is there something like the inertial ellipsoid and the invariable plane, the pole and the hairpole? Stay tuned for the sequel.